All right, welcome back. So now that we have a little bit of a feel for what classification is and how this Cannon algorithm really works, a question you might be asking yourself is, all right, if we use Cannon, we have a choice of predictor. So we did points per game or turnovers per game. Which one of those might be the better predictor to use? We also have the choice of k. So k could be really any positive integer. And so what value of k is really better in our particular setting? To answer those questions, what we are really hoping for is that our Cannon algorithm has as many correct classifications as possible. So the idea with this is that for those 10 players that we were predicting whether or not they made the All-Star team or not, if we have some actual data on whether they actually made the team for that year, so that's in this column here called All-Star, and so Bates Diop did not make the All-Star team, Olynyk did not, Martin Jr. did not, Durant did, Looney did not, Markkanen did, LeBron James did, and then these last three did not. What we could do is we could compare whether or not they actually made the team to what our Cannon model predicted they would. And so when we had set k to be 1 and when we had used points per game as the predictor, these would be the predictions that you would get. So not All-Star, 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 not All-Star, 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 and then the last three are predicted to not be an All-Star. Again, what we're hoping for is that if the algorithm is good, then a lot of these will match up. So it correctly predicted that Bates Diop was not an All-Star, but it missed Olynyk. So it predicted Olynyk would be an All-Star, even though in actuality, he did not actually make the team. One very common way to summarize this type of thing is to build a confusion matrix. And so a confusion matrix has whether or not players made the All-Star team as the rows, and then it has what the Cannon algorithm predicted them to be as the columns. And so to populate this confusion matrix, Bates Diop was not an All-Star, and the algorithm predicted that he wasn't an All-Star. And so he goes down here. And so this changed from a 0 to a 1 because he wasn't an All-Star and he was predicted not to be an All-Star. Then Olynyk was predicted to be an All-Star, but actually he wasn't. And so that he goes in the spot here. He's not an All-Star, but the Cannon model predicted that he was, and so he gets populated there. Same with Martin Jr., and so that bumps up from a 1 to a 2. Durant was an All-Star and was predicted to be an All-Star, and so he goes in the upper left. All-Star predicted to be All-Star. And you probably don't want to watch me walk through all 10, but it repeats for all 10 of those players that we were making predictions for. And our confusion matrix winds up looking like this. Based on this confusion matrix, we can calculate the most common metric used to evaluate these Cannon models, which is the classification rate. The classification rate, once you have the confusion matrix, is actually fairly simple. All it is the number of correct classifications you've made divided by the total number of classifications you've made. So here, these three are correct because they're All-Stars that were predicted to be All-Stars. These 5 are not correct because they were not All-Stars and we predicted them to be not All-Stars. And so we have 8 correct classifications, 5 plus 3, divided by 10 total classifications that we're making. And so our classification rate in this little example is 0.8. The higher the better. So we want our classification rate to be as high as possible. If we repeated that using k equals 7, and so now I'm classifying those 10 players using the 7 nearest neighbors, still with the points per game variable, we get some new predictions in this last column, and we could remake the confusion matrix, this time using k equals 7. If we do that, we actually get a confusion matrix that has everyone classified correctly. So in this case, k equals 7 is better than using k equals 1, because we get a higher classification rate when we use k equals 7. So to get some practice with this, you should go back to the worksheet and see if you can make a confusion matrix and calculate the classification rate, but this time using the turnovers variable as the predictor instead of the points per game predictor that we used in this video. And so you should be able to see if turnovers is a better or worse predictor than points per game for a couple of different values of k.